to Luca McKinnon, and please, Rodrigo Carvajal, be ready for the next one. You're not on mute. Wait a minute. There you go.
Cool. Hi, everyone. My name's Lucas. I'm based at Imperial College London, but this happens to be a project based here with Ben and Justin Elsing at Stockholm University. And this is sort of a recent technical advancement. This is a little bit more towards the ML side, but it's an example of how sort of sitting down and thinking about a problem can improve some bottlenecks in existing machine learning architectures. I'll talk about some cosmological implications for this framework tomorrow. But if your data, in whether it's cosmology or proteins or supernova, whatever it may be, looks sort of like a cloud of points, you have a catalog of things, whether or not you can connect them in a graph where you're dealing with sets, somewhere in your analysis, you're going to have some sort of information aggregation. So you're going to sum up either these points or the embeddings. You'll take a mean, you'll take a variance. You'll look at some moment of this distribution and hopefully learn something from it. So that's all graph networks really are. Is you learn some embeddings, and then you have to aggregate them together. And if you fix that aggregation, you can be susceptible to changes in the underlying data distribution. So it's worth taking a look at something like linear regression, where you can describe this collection of points at the level of a likelihood. So this is a likelihood we happen to be able to write down. And if you take a look at just the derivative and the second derivative, which we call the score and the observed Fisher matrix, you notice they have this nice additive structure. And if you take a look at the symmetries of these two pieces of information, this one is just a vector, and this is just a set of weights of this dimensionality squared. So we can encode the symmetry into information aggregation. And if we do this, you can either pull apart the loss function to take a look at what the network's learned at the level of the information matrix, or you can just drop it into existing graph network applications. In a linear regression example, encoding this full description of the underlying distribution improves your information extraction, even when you're changing your global information distribution. So you can train it on some uniform distribution and then submit it, test it on something that's out of distribution. And then in graph scenarios, this does improve information extraction on common benchmarks. And I'll talk about some cosmological applications tomorrow. So please feel free to contact me with any questions, chat with me afterward. Thank you.
Thanks a lot.